Hello wonderful person, this is Anton, and in this video we're going to be talking about what seems to be the final confirmation of at least one intermediate black hole we discovered somewhere out there. This is actually pretty exciting because we've been looking for these types of black holes for a very long time. So for several decades now we've been trying to discover at least one intermediate sized black hole and confirm its existence. But it turns out these are really elusive and extremely difficult to identify. One of the mysteries regarding them is actually why they're so hard to find and why they seem to be almost completely invisible even though we think they're pretty much everywhere around even our own galaxy. But what exactly are these black holes and why are they so special? Well, they're basically in between the really small, really common types known as stellar-sized black holes and the really massive black holes in the middle of various galaxies known as supermassive black holes. Just to give you a size comparison, this right here is an example of Sagittarius A star, which is the black hole in the middle of our own galaxy, and here's how all of this compares to planet Earth. Our planet is actually ridiculously tiny in comparison to this black hole. It might be a little bit easier to see if I change the background color because this really shows you how tremendously massive and large these black holes are. Then we have much smaller black holes which are really common, known as stellar-sized or stellar mass black holes, and these are typically only a few kilometers or a few miles across. Here's one that's only a few miles or a few kilometers in radius. I think it's about actually 3 kilometers, which makes it one of the smaller black holes we know that exist out there. And these are pretty common, we've actually seen a lot of proof of their existence, but in between the tiny ones and the giant ones, there are these other black holes known as IMBH or intermediate mass black hole. And in terms of the actual size, they would be very close to a planet like Jupiter or Saturn, with masses in around thousands or tens of thousands masses of our own sun. The one we just discovered, or actually the one we just confirmed, has a mass of about 50,000 masses of the sun, giving it the total size of just a little bit larger than Jupiter, but obviously with 50,000 masses of the sun on the inside. But like I mentioned, they seem to be really rare or really difficult to find. And as of 2020, the evidence for these black holes was actually not really that good. For example, we've discovered several stars moving extremely fast across the galaxy, and the only explanation to this velocity was if they were actually kicked out from the galaxy by the interaction with an IMBH, with intermediate mass black hole. But in some sense, I guess this is not really a very good explanation. There could have been some other effects that caused such a high velocity. Also, a few months ago, scientists noticed that there was an unusual, really fast moving gas in the middle of our own galaxy that was actually moving a little bit faster than it should. And it seemed to have been moving around an empty spot in the middle, which of course suggested that something really massive was there. Scientists assumed that it was probably an IMBH as well. So probably just an invisible black hole somewhere in the middle causing this gas to spin so fast, but once again, the evidence so far is really circumstantial, not really that good. But now, for the first time ever, the scientists were actually able to confirm at least one of these objects in a galaxy relatively far away from us at a distance of about 740 million light years away. Now, this is what they saw. This is actually the original detection from 2006 when we detected what seemed to have been really powerful X-ray burst. But this burst was not just a typical burst, it indicated something was being destroyed. And although technically this could have been anything, even a neutron star causing this, because this burst lasted for so long and because we were able to use Hubble telescope to confirm that the actual energy released was really high, the only plausible explanation that made sense was this right here. It was very likely an IMBH destroying a star and creating a tremendous amount of energy in the process. This is exactly what we've been observing for the past 14 years, and this is what these scientists think is still happening there right now. So essentially, by ruling out every other explanation, the only possible explanation left here was that this was literally a black hole destroying a star. It could not have been anything else, and right now the scientists are pretty confident about this. And it was really the combination of the X-ray data and also the visual data that allowed us to see what's really happening here and analyze it very thoroughly. Also remember, this is pretty far away, 740 million light years away. So seeing such a powerful and long event only meant that something really large and massive had to create it. But this doesn't change the fact why these black holes are so difficult to find and why we're having so much trouble identifying more of them, because we have found quite a lot of other black holes out there. And one more piece of confirmation here was the location of this black hole. It was actually not in the galaxy itself, it was more on the outskirts, kind of where we expect to find these intermediate black holes to begin with. And we think that it probably came from the typical globular cluster that we find in various galaxies, including our own, orbiting around the galaxy itself. Here's an example of a globular cluster from the Milky Way galaxy, and we have quite a lot of these. Many galaxies possess them, and today we believe that these are very likely remains of older dwarf galaxies that essentially made the Milky Way. Basically the leftover pieces from the initial absorption of other galaxies. And inside of these globular clusters, we also believe many of them do possess intermediate-sized black holes that were initially inside the dwarf galaxies. So we think that this is exactly the type of a black hole that generated this destruction of a typical star. And because, as you can see, there are so many different stars here, several million as a matter of fact, it's no surprise that at least one of them would approach really close to the center and get destroyed by the relatively massive black hole in the middle. So this is kind of what we think happened in this particular situation as well. And it also means that we're probably going to be seeing more of these typical emissions and a lot more of these IMBH black hole swallowing stars in the near future, because now we kind of know what to look for. But this of course doesn't answer the question of some of the other mysterious black holes possibly in the middle of our own galaxy that we've detected in the last few years. And we obviously still have no idea on how these black holes are generated and what their origin is. For a black hole to become so massive, basically a mass of about 100,000 masses of the Sun, it does need to experience some sort of a really cataclysmic event, or possibly a lot of collisions. Now we don't really know how this occurred and what happened to these black holes, but for now we're kind of curious to see where they're kind of located. Or more specifically, where can we find more of these black holes to study them in a little bit more detail. And we also are not even sure if every globular cluster out there has them. We think some do, but right now there's really no proof. But at least now we have a confirmation that they do seem to exist, and they do seem to act as we think they do, while at the same time being located in the region of the galaxy where we kind of expected to find them. Hello wonderful person, this is Anton, and in this video we're going to be talking about black holes once again. But more specifically about this new incredible discovery and a new study that created a technique allowing us to see extremely distant black holes in a way we couldn't actually see before. Okay, not really see, not with our eyes, with X-ray radiation. Now, sometimes there are incredible new discoveries that become extremely sensational, like for example, the first picture of a black hole that we could see with our own eyes. And this is of course the most famous picture of the black hole known as Poehi inside the galaxy known as M87, and because we can see it with our eyes, I'm pretty sure most of you are already familiar with this. But once in a while, an incredible study comes up with another way of seeing black holes, but because there is no actual picture to show and it's really all just numbers and tables, it really kind of goes under the radar and nobody really talks about it. But this study right here that came out in Nature magazine is actually really impressive, just as impressive as the picture of M87 black hole. So once again, here we're looking at a distant black hole in another galaxy, the so-called central black hole. This one right here that you're looking at is a simulation in the middle of our own galaxy. This is our own Sagittarius A star, the closest central black hole to us. But pretty much most of the galaxies out there, with some exceptions, have these black holes as well. Some bigger, some smaller. But at a distance of about 1 billion light years away from us lies another really interesting galaxy, the actual picture of which you can see right here. And this galaxy has the name, well, this name. I'm not gonna read it too many numbers. But essentially, this is one of the more well-studied active galaxies known as Seiffert-1 galaxies that produce a lot of different emissions because the galactic nucleus in the middle, the black hole in the middle, is actually active. It's consuming a lot of matter, it's emitting a lot of energy, and has a very bright center in the middle that we can see from really far away. So this is what this galaxy is all about. But it's also famous because it has a tendency to change its brightness quite dramatically. Even over a period of a few days, it can go up in brightness so much that it will suddenly light up and become like 50 times brighter. And then, just like that, it will become really dim again, and this does change quite a lot. So it's a really fascinating galaxy for us to study because it will help us discover a lot of other secrets about black holes. But seeing a black hole at this distance is not easy. If you remember, the M87 black hole is only about 55 million years away from us. This here is almost 20 times as far away, so obviously things are much smaller. And the technique for using this, interferometry, cannot really be used at these distances. Something else has to be used if we want to investigate, study, and even create an image of this black hole. And so the scientists studying this realized that they could use the X-ray emissions coming from this black hole to try to understand what's happening here and possibly one day even create an image of the actual region around the black hole. But the technique that they used is not really difficult to understand. It's based on echolocation, or essentially reflections coming from the actual black hole that then create a sort of an echo that propagates throughout the universe and can be, I guess in some sense, heard or technically seen here on Earth. To study all of this, they used the amazing XMM Newton telescope that was launched about 20 years ago and is still very active, and this is the best X-ray telescope we have available. And so the idea here is that as the matter falls into the black hole and starts generating a lot of really powerful radiation, and of course X-rays, some of these X-rays will obviously go in different directions, but some of them will start interacting with the accretion disk itself and the corona around the black hole, the actual region of space around the black hole that has a lot of really highly charged electrons. And these corona that are present around various black holes, in a sense, act as, well, I guess walls in a typical room. In other words, they reflect various types of radiation and thus allow us to kind of see and understand what's happening in this region by looking at the actual echoes. And this X-ray reverberation technique is extremely accurate and helping us see not just the accretion disk, but also understand how fast the black hole is spinning, and most importantly, how massive the black hole is as well. And just to give you a funny analogy, just so you can kind of understand how this works, by now I think, if you've used a smartphone, you can usually pretty clearly tell when someone is calling you from a toilet. There's a certain echo that forms when the person speaks to you, and you sort of start understanding that they're actually inside of a smaller room. And normally, that room would be a bathroom. But let's just say you're a super smart scientist and you want to take this to the extreme. So by listening to their voice on your phone, and by listening to various echo that you hear produced from the actual phone call, you can then use the reverberations that you hear to reproduce, in some sense, the room they're calling from. So the echo itself and various properties of this echo will allow you to understand where this call is being made from. And this is pretty much exactly what the scientists did, except that it's not a bathroom, but it's a black hole 1 billion light years away from us, and it's not really voice sound, but it's X-rays. And one other major difference between the phone call and this is that the observation here was roughly around 5 years long, and in total they collected about 23 days worth of data. So this was a pretty long observation of these echoes and allowed the scientists to run this experiment several times. I think it was about 16 times, creating an amazing opportunity for the scientists behind this paper to test and retest their observations. And so what they've discovered is that this faraway black hole is about 2 million times the mass of our sun. In other words, it's about half the mass of the black hole in the middle of our own galaxy. But at the same time, it spins extremely fast. As a matter of fact, the scientist seems to have found out that it spins almost at the limit of how fast the black holes can spin, which is of course the speed of light. And this of course creates a lot of very unusual relativistic effects that we still are trying to kind of understand when it comes to these supermassive black holes. So basically here you can expect a lot of various time dilation effects and a lot of so-called frame dragging, which essentially means that here the time really passes super slow. And in some sense this is basically what Interstellar was about, the type of a time travel that black holes can create. But anyway, because the study was so successful at figuring all of this out and they've created this really interesting technique, we'll now be able to apply this to many other black holes out there, and it's very likely we're going to one day discover something even more incredible. But there were a few more discoveries in this paper, and I think one of the more interesting ones is that they've also discovered that the corona I previously mentioned that's around the black hole seems to shrink and change in size quite dramatically over a period of only a few days. So the actual area and actual volume around the black hole is extremely dynamic. These black holes can transform so quickly and so violently that it's very difficult for us to imagine what all of this really looks like. This right here is just a simulation. And one day, using the technique discovered in this paper, we might be able to simulate all of this in a little bit more detail to help us understand what's going on in these extreme regions of the universe. And lastly, European Space Agency's Athena that's going to come out in 2031 will allow us to use this technique with a lot more precision and probably see things even more clearly. But because 2031 is still kind of far away, we might be able to come up with even more interesting techniques to allow us to study black holes even better. And I'm really hoping that this technique one day will help us visualize what's happening here in a little bit more detail and someone creates some kind of an algorithm that will allow us to use these X-ray observations to create three-dimensional pictures or images that can then become even more famous than the picture right here. Hello wonderful person, this is Anton, and in this video we're going to be talking about the biggest explosion in the universe. Once again, because we just found something that was even more powerful. So it seems that once again we've discovered something that beat the previous record, and specifically here we're talking about the biggest explosion we've ever detected, or at least the signs of that explosion that very likely happened a few 100 million years ago. But before some of you say, but wait Anton, if that's even your real name, isn't Big Bang the biggest explosion in the universe? Instead of explaining it myself, I'm going to point you toward the videos of amazing Dr. Don Lincoln, who explains a lot of the Big Bang misconceptions really well. He's one of the major scientists in Fermilab, and he explains these concepts really well. So check out some of his videos to kind of learn more about why Big Bang is actually not an explosion at all, but more of an expansion event that's still going on. Yet there was a video that I made about 2 months ago that was actually called Discovery of the Biggest Explosion in the Universe, that was about, back then, the biggest explosion we discovered. But what the scientists discovered just now very recently beats this record by about 5 times. So the explosion event that happened in this region known as Ophiuchus is about 5 times as powerful as the previous record holder. Now this is why it's kind of exciting, because we never imagined such events to even occur. In a nutshell, all of this happened not so far away from us in the galactic cluster known as Ophiuchus. If we look at the map of the universe of nearby galactic clusters, this is roughly what all of this looks like. Our galaxy is inside the Virgo supercluster and is being pointed at by this arrow right here. It's really tiny in this image. And if you were to go this way for about 390 million light years, you will discover the cluster known as the Ophiuchus. And if you were to start zooming in on this, eventually you would discover this area here that's roughly a few million light years across. And this is exactly where the scientists just discovered what seems to be the signs of an extremely large explosion from the center going this way. And the reason they know that this is an explosion, or it was an explosion a few 100 million years ago, is because of the actual structures and the emissions happening here. There are a lot of X-rays coming out, and there are also a lot of radio emissions, all together forming in the same region in the same shape. As if something in the center suddenly exploded, releasing all of this energy, in a sense resembling a kind of a volcanic eruption on Earth, but here this is on galactic proportions, and the volcano itself is in the middle, and suddenly all of this energy came out of here and created this cavity that we see on the screen. And all of this was determined using various frequencies and a very thorough analysis that essentially presents us with a kind of a picture where something in the middle caused a tremendous release of energy that then created this edge that is otherwise almost impossible to explain. Whatever this emission was, it was so powerful that right here there's actually a kind of a hole in plasma that's otherwise present around the galaxy, and this super hot gas created an actual discontinuity right here, and it's visible in every spectrum. In terms of the actual size of this, I guess you could call it crater or a galactic crater, it's about 15 Milky Ways across, or essentially several million light years across, which makes this a tremendously large and very unusual formation. But obviously we've seen many other outbursts and explosions in other galaxies, but normally they're not really even close to being as powerful. What we saw here is equivalent to roughly around 50 billion supernova. Now it's obviously very difficult to imagine such a huge number, but if this is just one supernova, and this here is about 10 supernova, now multiply this by a billion. Anyway, it's really difficult to imagine such a huge amount of energy being released, but this energy, as it was released, essentially created this unusual formation. And obviously we don't really know why, how, or what created this, or how this was even possible. We obviously suspect the supermassive black hole in the middle, but the amount of mass that this black hole had to actually consume suddenly is kind of difficult to explain. Although actually the scientists don't think that this happened suddenly, they believe that this was probably over a period of several million years. So it's quite possible that something really massive, like for example some sort of a massive gas cloud, was absorbed over a long period by a supermassive black hole and created this really large emission. And one of the reasons we've only discovered it now, even though it's so close to us, is because we never really bothered to look at this particular galactic cluster in radio waves. We always either looked at it in X-rays or in visual light. But now the scientists decided to take a look at it using radio waves as well, and this is when they saw this unusual formation that was present both in radio waves and also in X-ray radiation as well, and both emissions were more or less aligned with each other, forming this unusual crater-like shape. Now right now we obviously have no explanation for much of this. This is only just an interesting discovery. There's really no actual ways to explain what exactly causes such events, or if such an event can happen in our own galaxy, or if this even had any influence on our galaxy. But nevertheless, this is still interesting to us because currently this galaxy is extremely quiet. It's a very, very quiet radio galaxy that still has an active galactic nuclei, but in comparison to some of the other galaxies, and even in comparison to its own past, it's extremely, extremely low in luminosity, and it doesn't produce as much radiation anymore. And so the scientists now think that because of this huge explosion, whatever happened back then, this galaxy sort of made itself extremely quiet. It sort of expelled a lot of material that was around it, creating something that's a lot more quiet now than it used to be before. And this is what they believe may have happened approximately a few hundred million years ago. And if these large explosions can change galaxies so dramatically, this actually means that some galaxies could be completely destroyed by these large explosions. And if these large explosions can actually quiet galaxies, what if they can also destroy them? What if an emission can be so powerful that it can totally blow the entire galaxy apart? Now this is something we've never seen before, but we obviously haven't really looked that hard yet. I'm sure it will take a few years, but we'll probably discover even more signs of even bigger explosions out there. And interestingly, when the scientists originally found this, they actually kind of didn't even believe that this would be a powerful explosion because it was just way, way too powerful to exist. It took a lot of follow-ups and a lot of additional observations to finally admit that what they were looking at was what seems to be the most powerful explosion we've ever seen anywhere. And it doesn't seem to be that far away from us either. It's a lot closer than any of the previous findings. Now, if something like this ever happened in the Milky Way galaxy, chances are a lot of gas and a lot of stars would just completely disappear or at least get kicked out of the system. And since we see that such explosions are even possible in the universe, it also kind of slowly takes us closer and closer to answering the questions about why we're not seeing any extraterrestrial intelligence out there. Our universe seems to be a lot more violent and a lot more unpredictable than anyone ever imagined. If such an explosion occurs near our galaxy, I'm pretty sure that most of the life on our planet would perish really quickly. And so maybe the answer to Fermi paradox is that we are really, truly the only survivors in this madness of the universe. Hello wonderful person, this is Anton, and in this video we're going to be talking about a correction to the study I've talked about a few months ago when the Chinese astronomers claimed to have discovered the so-called impossible black hole. So a few months ago I released a video where I talked about the study from China that actually described the discovery of the so-called impossible black hole. The black hole that shouldn't technically exist. Now, when it comes to black holes, we think that all kinds of black holes exist except for this very specific type, or more specifically, the black hole of a certain mass. And here we're talking about a mass of about approximately 50 masses of the Sun, up to about 120 masses of the Sun. Now, this gap is created by the fact that we think when a star, such as for example the very well-known Eta Carinae stars, when they explode, could technically explode completely. They shouldn't really leave any remnant behind. In other words, we usually refer to this as pair instability supernova. Basically, a certain star will explode entirely. It will create such a powerful supernova that nothing will be left behind. And from all of the calculations over the years, we established that black holes between the mass of about 50 to 120 masses really shouldn't be possible, unless of course two smaller black holes collide. Now, when the original study came out back in December of 2019, the Chinese scientists speculated that what they've discovered was essentially a black hole known as LB1 that was about 70 or so masses of the Sun, and it was orbited by another object, by a star, and the star was possibly about 8 masses of the Sun. And all of this was established by trying to analyze the distance and analyze the orbital parameters of these two objects. But several follow-up studies that were released pretty much within a few weeks after the initial release all agreed that, well, it's very unlikely that this 70 masses of Sun black hole exists. As a matter of fact, several scientists established that there were at least two major problems with the study. The first one was that the distance was overestimated. It's very likely that the distance to this system was not over 4,000 light years as originally proposed, but a lot closer to us, possibly about 2,000, maybe 2,500. At the same time, many scientists suggested that if there was a black hole of this type, and it was also orbited by a very massive, very bright star that we can actually see, it's very likely that this system would have a lot of various, very easily observable emissions, such as, for example, X-ray emissions, and nothing was observed from this direction. So either this was a completely unusual and unique object that we've never seen before, which is kind of unlikely, or these all studies were making a good point that this was not an impossible black hole at all. And the most recent study decided to investigate this even more thoroughly by actually looking at the emission spectra of what's really happening around the star itself. Not the black hole, because we can't really see it, but the star. And they wanted to analyze what is the star made out of, because this is something we can use to establish what sort of a system this is. And the scientists behind the study, you can find it in the description below, did a very thorough analysis of all of the elements inside of the star. And pretty much right away they discovered something really unusual. There was quite a lot of helium emitted from the surface of this star. And that's something we really don't expect to see in most of the stars. Mostly because, obviously, for the most part, the top of the star, all of the surface here, should be hydrogen. The helium and other materials like oxygen and carbon are inside of the star, and this is where essentially the burning itself happens. Basically, if you were to look at our sun, the actual nuclear reaction, the fusion of hydrogen into helium, happens inside the core. And all of the energy then propagates to the radiative zone, but everything here on the surface is hydrogen. And a lot of this hydrogen actually stays as hydrogen and never really gets used up. This is why our sun, in a sense, is not particularly efficient, as are a lot of other really large stars. So all of our sun's helium is inside the core. We're not going to be able to see it if we look at the sun. So how is it that we're seeing helium coming from this unusual object? What's going on here? Well, there are certain stars known as helium stars. There are even stars known as extreme helium stars. And these objects, for the most part, are not really created normally. We think there are several ways that they can be usually created. One of them is, of course, if two smaller objects, like for example a typical white dwarf such as nearby Sirius B, or essentially what our sun will become one day, collides with another white dwarf, and because they do contain a lot of helium and a lot of things like oxygen and carbon, they can initiate helium to helium fusion and generate a completely new star. Basically, they start the burning reaction by combining the material from two separate objects. If their mass is less than about 1.3, 1.4 masses of the sun, they don't explode, they don't go supernova, they just create a relatively active, very bright, very hot, but also helium or extreme helium star that also burns really quickly. It actually uses up its energy relatively fast. But then there's another way, and this is what the scientists think may have happened here. The other way is if a typical star essentially gets all of its outer shell, all of its hydrogen slowly sucked away by the object orbiting around it. Now this could be a neutron star, this could also be a black hole, it can also be a white dwarf, and even a typical, slightly more massive star can do this as well. Essentially anything can be this, you can call it vacuum cleaner, that sucks up all of the hydrogen and exposes the inner core, the helium core. And then what remains behind, if the star was initially big enough, is a helium star that now starts burning helium and creates a lot of energy that way. And the thing is, the scientists behind this paper believe that this is exactly what they're observing here. Basically, it's a stripped helium star, and it's more likely that if this is a stripped helium star, that it's not going to be as massive as reported by the Chinese scientists. The actual estimates, at least according to all of the other models of helium stars we have, is that the star itself probably has a very similar mass to our own sun, maybe a little bit more massive, about 10% more massive, and the object around which the star orbits, the object known as LB1, could be about 2 to 3 masses of the sun. In other words, it's either a really tiny black hole, which is very unlikely, or more likely it's some sort of a neutron star, or possibly even just a regular star that's not very bright. So in other words, this could be any object, really absolutely any object out there, even just like a really dim star that's very difficult for us to see, and this star has about 2 to 3 masses of the sun. Although the current assumption is that it's probably a neutron star, and it's a neutron star that's not active yet, simply because of the distance between these two objects. But don't get me wrong, this doesn't mean that this is not an exciting system. It's still an exciting system simply because of the star that they discovered. These so-called helium stars, or the extreme helium stars, are very rare, and we do want to understand how they form and what exactly happens to these stars at the end of their lives. For now, we don't unfortunately have enough of them to analyze, and because we believe their formation is such a rare event, it's a lot more interesting for us to discover a helium star than it is to discover invisible and potentially not even real black hole that's out there. And because most scientists pretty much agreed that the black hole itself very likely either doesn't exist or is a lot smaller than initially reported, in this case it's really all about the star itself. And since the scientists definitely saw the signs of helium on the surface, this really makes it more likely to be a helium star than anything else. If this system has a helium star that's a lot more massive than a typical helium star, that's even more interesting to us than a black hole. It really just raises a lot more questions about how stars are created, how stars survive, and how such unusual stars can even form in these binary systems where we don't really expect them to exist. But I think the most important lesson out of all of this is the scientific process. And this is actually really the main goal for this channel. My goal here is to try to explain how the scientific approach works and how most scientists would never really say something with an absolute fact. Today we understand that the only certainty is the uncertainty. And the way that we learn things and the way we understand things is by trying to see and analyze the world around us, making a few assumptions, trying to understand if this is exactly how the world works, and testing various theories. And if those theories come out true, then, well, I guess maybe this is how the world works. But if those theories come out wrong, then we have to abandon the ideas and try to come up with something else. This is probably the most important way of analyzing the world around us. And honestly, people that often make very strong statements and even live by those statements are very often, unfortunately, wrong. It's not really the way that we're meant to learn about the world around us. There's absolutely no way we can say something with certainty today, because there's a very big chance that things that we're saying with certainty today might be completely wrong in the future. I mean, think about the science in the past 200 years. In the past 200 years, our science has changed completely. What we believe to be true, like for example Newtonian principles, today are seen as, in some sense, not particularly satisfying. Einstein's theories are good, but once again, there's still things missing there. So we need to constantly challenge ourselves and try to revise our theories at all times. And this doesn't just include science, it includes pretty much everything around us. This is really how I try to live my life, and it is sometimes difficult to not know things for certain, but eventually you kind of get used to it. Hello wonderful person, this is Anton, and in this video we're going to be talking about the M87 supermassive black hole, but this time about the jet that it creates. Because a very recent observation and a very recent scientific paper discovered that, well, actually rediscovered that the material in this jet appears to be moving really fast. As a matter of fact, it appears to be moving faster than the speed of light. Huh? So when it comes to the faster than speed of light travel, we know that nothing in the universe can actually travel faster than the speed of light. Or can it? Well, the idea of superluminal motion does not necessarily violate laws of physics. Because even though nothing can physically travel faster than the speed of light, there are certain things, or certain, I guess, phenomena you can call them, that do create faster than the speed of light motion in terms of the actual appearance. In other words, sometimes the light creates a very unusual visual illusion where it does appear to be traveling much faster than it should be traveling. One of the best examples is actually the so-called light echoes created by this beautiful star that you see right here. But we're going to be talking about these light echoes and other superluminal motion effects in another video. So make sure to subscribe because this video will be released relatively soon. But a somewhat more complicated effect is created by various black holes and pulsars when their jets travel really fast, and when they seem to be pointed not exactly at us, not at 90 degrees, but at just the right angle toward us. And so when the black hole in the center of the galaxy creates a very powerful jet, and it's pointed at just the right way at us, it can occasionally, or actually most of the time, appear to create these effects of faster than light travel. So first, let's go through the physics of how exactly this works. Actually, we don't really need physics, we just need a bit of trigonometry. A wonderful person by the name of Sihat Kidris provides a pretty good explanation of what's really happening by using this really simply drawn illustration. So this right here in the center, point A, is the black hole. That right here on the right is us. And at point 0 we're going to release one of the photons and it's going to travel toward our planet. Then about 100 years later, this light will have reached the point D, so this distance here is exactly 100 light years. However, if a jet from a black hole is traveling at the speed of about 0.9 speed of light, it's only going to travel about 90, or actually not about, exactly 90 light years. So this is 90, this here is 100. Now, to find this distance CD, we have to use a bit of trigonometry. It's essentially the hypotenuse here multiplied by the cosine of the angle, which in this case is 15 degrees. And then we take that and subtract 100 from it. So what exactly are we going to get here? And a quick Google calculation gives us the value of about 13. So this here is 13 light years in length. Now, what about this distance? Well, to find this, we once again use trigonometry. Hypotenuse is here, this is the angle, so we have to do sine 15 multiplied by 90 to get the value of about 23.3 light years. In other words, technically, even though the light has only traveled 13 light years, it will appear to have traveled 23 light years, suggesting that this here is faster than light motion. Now, it might not really come to you right away because it is a somewhat tricky concept, but by the time photon 1 and photon 2 get to Earth, the light will give an appearance of traveling at 1.8 the speed of light. In other words, the light itself seems to be traveling faster than the speed of light. Now, we know this is impossible, and the trigonometry behind it explains how all of this works. And so now let's get back to M87 and its jet. Well, over the years, specifically for about 30 years now, the scientists have been actively studying various chunks of matter coming from the astrophysical jet itself. And in order for these jets to be created, some of the matter has to actually infall toward the black hole. And as the matter falls toward the black hole, some of it is going to end up inside the black hole, but some of it will actually get accelerated by the magnetic field and end up in one of the jets. However, despite our simulations showing them as somewhat, I guess, linear and continuous, as a matter of fact, this is a very beautiful jet right here, in reality, the jets are much more irregular and are made up of clumps and different knots that can easily be seen in different images created throughout the years. This here was created in radio waves. We also have very similar observations in visual light, and now the scientists have also created observations in the X-ray using the Chandra Observatory, and this allowed us to very accurately calculate the superluminal velocity, allowing us to estimate the actual speed of the particles inside the jet. To do this, they looked at two different observations from 2012 and 2017 at two different chunks of matter. And then looked at various knots from a distance of about 900 light years up to about 2500 light years away from the black hole, and observed their progression and their changes. So this is a 5-year difference here, and even though it's a little bit difficult to see in this image, a much thorough analysis established how much these different knots inside the jet moved in these 5 years. And what they've discovered is that some of these jets were moving at about 2.3 times the speed of light, others were moving closer to about 6.3 times the speed of light. And once again, this is the appearance of motion, so this allowed the scientists to very accurately estimate the actual speed of the jet. And it's very close to about 99% of the speed of light, allowing us to very accurately estimate the speed of the jet and its particles. This also allowed the scientists to establish that the X-ray observations are very accurate in determining the speed of jet particles, and this technique will probably be used in other studies as well to try to calculate how fast certain particles move in other jets as well. Their other discoveries involved noticing that the entire jet kind of faded by about 70% in about 5-year time, suggesting that there's a lot of energy lost by these particles due to the radiation produced as they move around the magnetic field in this region. And when trying to compare this observation to the observation made by the Event Horizon Telescope, the scientists mentioned that, well, this here is kind of like looking at the rocket launch. Basically, this is the rocket itself. And as this rocket launches into space, we then get to see the actual rocket in flight. So this here shows us the path that all of these particles take throughout the universe as they're released by the black hole. And even though in some way this is not a groundbreaking discovery because we've known about these jets and how fast the particles are moving here, this here is a much more accurate calculation and the confirmation of how quickly the particles move when they're released by various black holes. And since this jet is not super long, it's only about 5,000 light years, much shorter than a lot of other jets in the universe, It seems that we got pretty lucky in being able to study it and in learning so much about it, because basically this is the closest such unusual jet to us. It's only about 55 million light years away. This is one of the closest galaxies to us, and this black hole is one of the biggest black holes nearby. So in that sense, we're just in the right location at the right time. Hello wonderful person, this is Anton, and in this video we're going to be talking about some of the recent discoveries coming from this wonderful object known as Markarian 231. Today you're going to find out a little bit more about this unusual quasar and also why it's sort of exciting. Now this video was actually requested by one of the wonderful Patreon supporters, and just like me, he was actually really interested to find out what else is happening with this unusual object known as Markarian 231. I've also been following this object for quite a while, mostly because, to date, this is the closest so-called quasar to our galaxy, and it allows us to actually study these objects in a lot of detail. But before I tell you more about this object, let's briefly talk about the history of quasars and why they're sort of exciting. So, back in the 60s, the scientists started noticing that there were a lot of really strange radio emissions coming from various spots in the night skies. And they were nothing like we've ever seen before. The actual spectrum of the radio transmissions or radio signals was nothing like here on Earth. And it wasn't aliens because it seemed to be too random and too natural, but at the same time they couldn't really explain what's causing these signals. And it actually took a really long time, 2 decades as a matter of fact, to finally figure out what they're looking at. And the quasar we're talking about today, we actually discovered this back in 1969, but we had no idea what it was. But then someone realized that what we're looking at here is actually a highly redshifted radio signal of common elements like oxygen, hydrogen, helium, and a lot of other things that are basically common here on Earth and in our galaxy, but they had no idea how to explain this. Some of the things were redshifted by about 50%, suggesting that either this was an extremely massive object that would be almost impossible to explain, or it was a really far away and extremely powerful object that was also very difficult to explain. So the scientists were actually stuck not knowing what these were up until about 1987. And most of this was because we didn't even know that black holes were actually real, or that galaxies could exist really far away. And finally in the 80s we figured out that not only were these actually really massive objects, these were really massive galaxies, but they were also extremely powerful in projecting their astrophysical jets right at us, through their supermassive black holes. In other words, these signals were nothing more but these extremely massive black holes creating a lot of radio signals. But turns out that only about 10% of all of the quasars are radio quasars. Over time we discovered a lot of other quasars, including of course ultraviolet and infrared quasars, which of course is one of the more common quasars as well. And it just so happens that the closest one of these objects is the extremely beautiful Markarian 231. This is a galaxy where you can actually see the actual galactic parts, but just like every other quasar, it's extremely bright in the middle. But this brightness is not optical, which is why you don't really see it as blinding or as really bright here. It's in infrared light. It's an extremely bright infrared quasar, and it is actually the brightest infrared object in the nearest billion light years away from us. And over time we also realized that there could be 2 supermassive black holes here. One really large one, about 150 masses of the Sun in the middle, and one similar to the one in our own galaxy orbiting around it. Although some of the recent studies are not so sure about this, but so far this is still the best explanation. And because of the relative proximity of this quasar, which is around 581 million light years away from us, it allows us to basically start understanding these objects with so much detail. We've never been able to study quasars as well as we can with this particular object. And mostly because all of the other quasars or their technical cousins known as blazars, which are even brighter, are really far away, at least 30 times farther away. Like for example, not so long ago we discovered the first ever really distant blazar at distances of about 13 to 14 billion light years away. That's at least 30 times as far. This, however, is our neighborhood in comparison. And in the last few years, we've discovered a lot of really interesting things about this quasar and, well, I guess by definition, other quasars as well. So some of them do produce a lot of stars like this one, and there's actually a very interesting ring around the center where approximately 100 masses of the Sun of matter creates new stars pretty much every single year. It also obviously produces a tremendous amount of energy. It's extremely well visible in infrared from really far away, and is basically one of the brightest infrared objects you can find in the night skies, which is why it's also known as ULIRG, Ultra Luminous Infrared Galaxy. It's also obviously really active, and back in 2017-2018 there was a really large emission that allowed us to study basically quasar emissions in a lot of detail, which also allowed us to calculate that the amount of energy released was about 10 billion times more than our sun every single second, with the actual material moving at around 97% of the speed of light, creating this tremendously powerful astrophysical jet that's visible from pretty much everywhere in the universe. And because of this, these objects are usually several thousand times brighter than a typical galaxy like the Milky Way, which is why we can usually see them from essentially the edge of the universe itself. But since all of these quasars are also kind of different, some of them actually peak in ultraviolet light, some of them have a predominantly infrared emissions, and some of them only have radio emissions, we're always really interested to find out how is it that they're so different and what makes them so unique. And this specific quasar is also really interesting because we've recently discovered something really unusual coming from the center of the quasar. These scientists, whose paper you can find in the description below, discovered really high-speed emissions of a lot of molecular oxygen, basically the same oxygen that we use to breathe here on the planet. Now, it wasn't really coming from the center of the quasar. It seems to have been actually located about 32,000 light years away from the center. In other words, more or less from the center of the disk itself. And this is why it's even more mysterious, because the oxygen was moving really fast. Here you can kind of see the speeds reported are over 1,000 kilometers per second, meaning that the oxygen was actually escaping the galaxy. And the scientists who discovered this now think that maybe this is actually also related to the sudden creation of the stars, because normally we expect typical active galaxies not to produce too many stars. But in this case, the oxygen flow seems to act as a kind of a coolant, and it actually cools down the gas material around the galaxy. And because the gas is now cooled by this oxygen flow, these stars now get a chance to be created. But they also potentially have a lot of oxygen in them. Although as of today there's really no explanation for why this oxygen is moving so fast, where it came from, or what exactly it's doing to the galaxy itself. And in case you were wondering how they actually know this is oxygen, it's by looking at the radio emissions, and here they detected the emissions around 118 GHz, which corresponds to the emissions of oxygen, but this one was actually redshifted, allowing it to go through our atmosphere and thus be detected here on the planet Earth. Normally it's actually difficult to detect oxygen from Earth because a lot of the emissions get absorbed by our atmosphere, but if an object is really far away and its emissions are redshifted, it actually goes through the atmosphere and can be seen with typical telescopes. And this is exactly how they discovered so much about this quasar. Now, for now, this is the first detection of such unusual event coming from a quasar, but in the last few years we've learned so much about these objects. Like, for example, one of the coolest discoveries was that it turns out a lot of quasars are actually aligned in a certain rotation along the so-called cosmic web produced by various types of matter, including dark matter. And this was one of the biggest discoveries about quasars in the last few years. And now we're learning more about them. So I think in the next few years we'll discover so much that we'll finally be able to understand how all of this actually affects life here on Earth as well, and most importantly, how all of this might affect life on our planet when our own galaxy occasionally becomes a quasar or an active galactic nuclei galaxy as well. In other words, all of this is really important for us to learn more about how life was created on Earth and how all of this influences the evolution of life as well. But for now, that's all we know about Markarian 231. It's definitely one of the most fascinating quasars out there, and it's definitely going to be in the news a lot more once we discover more about this unusual object. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very fascinating topic of quasar tsunamis. And that does sound like something extremely powerful and extremely dangerous. So honestly, quasars are always fun to talk about, mostly because they're still quite mysterious. Because, you know, from, I guess, a few decades ago when we originally saw them as these really bright stars and we couldn't really figure out what they were, to the discovery that they're extremely powerful and extremely massive galaxies, which a lot of scientists didn't even believe at first, to then discovering that a lot of this power comes from these ultra-massive black holes in the middle that are absorbing so much mass that they produce a tremendous amount of energy and essentially this blinding light that creates brightness that's brighter than approximately 1,000 galaxies combined together. While at the same time, with so many different quasars out there, we're always kind of fascinated about different connections between them, what they actually represent for the evolution of the universe itself, and the more important question here is in regards to how this evolution of galaxies may have influenced our own galaxy as well. So in other words, has our own Milky Way been a quasar at some point in the past, and what did this do to our galaxy? And as we'll learn more about them by looking around the universe and discovering more of these quasars and the interaction they have with the galaxy itself where they reside, we realize how extremely powerful these events or these things, these objects are, and how they actually do influence not just the galaxy where they reside, but everything around them as well. Not to mention, we've also been discovering all sorts of connections between the, for example, galactic web or cosmic web and the position of quasars across the universe. So there's definitely a lot of really interesting things when it comes to quasars. It's one of the most fascinating studies in cosmology. But this recent paper that came out only a few weeks ago talks about something else that we kind of expected, but never really to that extent. And specifically here we're talking about what's known as a quasar tsunami. And as you can probably imagine, just as scary as it sounds, it's something extremely powerful and something that does influence the entire galaxy dramatically. Now quickly in a nutshell, so a quasar is essentially an extremely hungry galaxy, or technically galactic nucleus. The center of this galaxy usually possesses an extremely powerful black hole that starts eating up so much matter that it essentially just explodes with energy. It starts producing so much energy that it generates these really powerful winds that influence the rest of the galaxy as it keeps absorbing more and more matter. But as the matter falls into the black hole and generates a lot of this energy that's then exposed, this so-called galactic wind, or I guess you can call it quasar wind, becomes so powerful that it actually starts to influence the rest of the galaxy, in most cases causing a lot of the star formation to completely stop. Now this is something we kind of expected, but the recent paper used Hubble telescope to analyze 13 different quasars and discovered that some of these quasars are so powerful that they go beyond disabling stars. They create conditions that are essentially really extreme. For example, they generate such powerful winds that the material from within the center starts moving at approximately 6% of the speed of light and moves across the galaxy, colliding with everything on the way, first generating a lot of X-rays and a lot of ionizing UV radiation, essentially radiation that would probably strip any planet of atmosphere, and then slowly transforms into visible light and even infrared light. So essentially it creates this kind of a firework of different frequencies that are visible from really, really far away, and all of this is huge. It's the size of a whole galaxy. It's at least several thousand light years across. So it's almost the size of some of the smaller galaxies. They've also witnessed one of the quasars exhibiting a tremendous increase in energy that actually accelerated the wind by about 6 to 7%. So essentially it was moving at about 6% of the speed of light, and then the speed of this wind increased by about 3 million miles per hour, or about 4.5 million kilometers per hour. All of this within relatively short time frame. So this is something that we really didn't expect to see. This is how extremely powerful quasars and these active galactic nuclei are in general. So they do produce tremendous amounts of energy that influence the rest of the galaxy. And so by observing different quasars, they've established that there were a lot of different effects here. A lot of really, really strong and powerful winds, essentially causing the entire galaxy to kind of expand and inflate in some sense. And this is literally why the scientists behind this paper called this a quasar tsunami. It was a huge wave of really, really powerful, extremely high in energy material that was moving across the entire galaxy, slowly pushing everything aside, slowly destroying everything on its way, or at least influencing a lot of these stars in such a way that no new star could be produced, and very likely a lot of planets would probably be completely stripped of everything. And it seems that a single quasar, similar to the ones they've looked at, usually can easily push out approximately several hundreds masses of the sun every single year, and a lot of this mass ends up being in the intergalactic space. Now some of it might actually eventually come back to the galaxy, which is what we believe happens in most cases. In other words, some of this gas will kind of move away and then slowly get attracted back to the galaxy and then re-enter and possibly create new stars afterwards. But some of this gas might also end up in the intergalactic web, in the cosmic web, and be trapped there forever. So we're not really sure how all of this really influences galaxies, but it does explain why we don't usually see large massive galaxies as often as we would like. We do see a lot of smaller galaxies, and in most cases there is actually a correlation between the mass of the central black hole and the size of the galaxy. So what this all means is that the actual black hole in the middle controls the size of the galaxy. It actually prevents certain galaxies from growing too large, and also prevents some galaxies from having too many stars. And the more active the black hole becomes, the larger it gets, the more likely the galaxy is not really going to possess too many stars and too much mass. Most of it will probably get expelled. At the same time, this also explains why in most cases we see that star formation happens in bursts and usually around the same time. Like for example in the Milky Way, we know that these bursts created most of the stars. The vast majority of other stars, there were only very few stars that were created in the Milky Way galaxy in between these bursts. Now, we think our sun was actually also produced during such bursts, but for the most part, we never really understood what's really stopping these bursts from happening more frequently. And these scientists and a lot of other scientists suggest that it's actually the active galactic nuclei. Now, we don't think our Milky Way has ever really been a powerful quasar, but we do know that there were a few cases or a few times when our galaxy did experience the active galactic nuclei bursts. More specifically, not so long ago we discovered these so-called Fermi bubbles, which seem to be the leftovers from one such experience when the black hole in the middle of our galaxy started absorbing a lot of mass and created these really large and powerful emissions. Now, it may have not really been a true quasar, or at least not a quasar that would be really bright as some of the ones we've just observed, but it might have been enough for it to kind of look like this, like a typical quasar from a distance, while at the same time it did probably stop a lot of the star formation in the galaxy for at least some time. But we haven't really experienced any major bursts since then, and this was probably a few million years ago. So we don't really know what causes these bursts to occur afterwards. This is yet another mystery of the universe. Or we don't actually know what causes stars to suddenly start forming in between these galactic bursts. Or we don't actually know or currently understand what causes sudden bursts of star formation in between these very powerful galactic bursts caused by black holes. But it is something we would really like to learn more about, because technically, if such an event occurs in the Milky Way galaxy, there is a really high chance it's not really going to make our Earth any more habitable. So these events are really important for us to understand and for us to actually learn about, especially because in the last few years we've discovered that our own black hole in the middle of our galaxy seems to be getting a little bit hungrier. It's been increasing in brightness over the past few years, and we can't really explain why just yet. So we're secretly hoping that this is not the beginning of some sort of a major quasar event or any other event that could potentially cause problems for humanity. Although currently we don't really think that anything like this is going to happen anytime soon. There are just no signs or no evidence to suggest that our galaxy is going to become a quasar anytime soon. But this doesn't mean that we should stop learning about quasars. This nevertheless is a very fascinating topic and does teach us a lot more about the universe in general. Hello wonderful person, this is Anton, and today we're going to be talking about a new discovery coming from the center of various galaxies. Specifically, these so-called active galactic nuclei, which we just discovered are really important in creating something absolutely crucial here on Earth. So this beautiful picture that you see right here was taken by Hubble a few years ago, and this is essentially the astrophysical jet, very powerful jet produced by the beautiful M87 black hole, by now the most famous black hole on Earth. And this astrophysical jet is part of the so-called AGN, or active galactic nuclei. We usually refer to these central regions as active galactic nuclei when there's a lot of energy being generated that can be seen from really far away. There are quite a lot of famous galaxies that have this, and the closest and probably the more interesting galaxy is the one we can easily see in our night skies if we have a radio telescope. So right here you can't really see it, it's very difficult to see it without a telescope, but as soon as I change things to radio waves you'll see it right away. This is the so-called Centaurus A galaxy, with very pronounced astrophysical jets which are the result of these very powerful emissions coming from the center. Now we know that our own Milky Way also had these emissions, And we know so because we've discovered these so-called Fermi bubbles emanating from the center of our galaxy. This is kind of what they look like, and these are the remnants of so-called AGN activity. In other words, once upon a time, the Milky Way galaxy was doing this as well. And this was probably a result of a galactic collision which suddenly added a lot of mass to the center. This is how we believe most galaxies become so-called AGNs. Usually this kind of an event lasts for up to about 1 million or roughly around 1 million years, and these events happen every 10 to 100 million years. Normally it's caused by galactic collisions, but it could also be caused by a sudden increase in mass in the center of the galaxy from some sort of other collision, like for example with a really huge gas cloud. Approximately 10% of the life of a galaxy is essentially as an AGN. So for a galaxy like Milky Way, it may have been an active galactic nuclear galaxy for over 1 billion years, or possibly even up to 2 billion years. And the last time the Milky Way was an AGN was only a few million years ago. In other words, these events are very common, they're very frequent, and turns out they're really important. And by the way, this is how most galaxies grow as well, including of course these supermassive black holes in the center. These collisions and these sudden increases in mass and the so-called AGN activity, or active galactic nuclei activity, is how galaxies become more and more massive. And we've always believed that during the AGN activity, a lot of galaxies would probably not have a lot of star creation, so basically the star formation kind of stops, while at the same time, if there was any life in the galaxy, it would very likely get completely destroyed, at least if this life was a lot closer to the central black hole. Now, it's also very possible that there are certain things that happen during the AGN activity that are essential to life, and the recent study that you can find in the description below investigated and discovered just that. Turns out that AGN, or active galactic nuclei, can easily create massive amounts of water and also various organic compounds. Compounds that are necessary for life to begin anywhere in the universe, while also generating really large amounts of water as well. In other words, the more AGNs a typical galaxy had, the more likely it's going to have a lot of organics and a lot of water circling around looking for a new planet to settle. So in other words, it's very likely that if it wasn't for these very powerful events that happened in the Milky Way throughout its history, there would probably not really be as much liquid water and as many organic compounds circling around. And thus, some of these compounds and some of this water would never really make it to Earth and create us, of course. But now we have to answer the question, how exactly does this happen and what does it have to do with these powerful events? Well, it turns out, of all sorts of powerful radiation that is produced during AGN, most of it is actually hidden by the dust cloud, and only some of it gets through to the other parts of the galaxy. Like for example, for M87, we didn't really see the black hole in most of the other spectra except for the radio spectrum. And so what we were looking at when we looked at M87 was the radio emissions. And if instead you looked at this using an optical telescope by zooming in quite dramatically, you would actually not see anything. You would only see a lot of gas. And so for the most part, we have to look at other frequencies. And it turns out that certain parts of the X-ray spectrum, specifically the so-called hard X-rays or the more powerful X-rays, can easily penetrate these clouds and also influence a lot of molecules in the vicinity. And so if by accident there was actually a molecular cloud that was about to form into various stars, these are the so-called star nurseries where stars are usually made. And this one specifically is from the beautiful Carina Nebula that you can see right here. So if these clouds were present during the AGN activity of our galaxy, the X-ray illumination would suddenly start changing a lot of molecules here, making a lot more water and a lot more organic molecules, many of which are crucial for life. And this is very likely what happened to the molecular cloud from which Earth and the Sun were created as well. It's very likely that the amount of water was increased and the amount of organic molecules was increased because there was a very powerful AGN event during the formation of our solar system. And these powerful outbursts could definitely modify a chemistry of any galaxy, obviously increasing the chances for organic life to develop. While at the same time, the simulations discovered that up to about 100 times more water and organic compounds were created during these AGN events. So it's very possible that these are absolutely essential for a typical galaxy to have enough water and organic compounds. And one of the ways that the scientists even discovered this is first of all by looking at various AGNs out there and discovering a huge amount of water and organic compounds that shouldn't really exist there, but also by running a computer simulation and placing a molecular cloud roughly around half the distance of our sun to the central black hole. In other words, if this is where we're located and the center of the galaxy is right here, then imagine half the distance. And at this distance, up to about 100 more molecules of water and organic compounds were created during the AGN. This also suggests that maybe we should be looking a little bit more at Centaurus A, for example, and trying to discover if there is a lot more organics and water here as well, and possibly some sort of a planet somewhere out there with potentially extraterrestrial life. And although we've always believed these eruptions were also quite dangerous for life, at least if you're really close to the central black hole, at the same time they appear to be absolutely essential for the formation of life as well. A bit of an irony, I guess. And it seems that it all is a matter of balance. If it's too strong, it's too dangerous. If it's too weak, it might not be enough to create enough water and organics for a planet like Earth to develop. But for now, it's a bit of a speculation, and we need further studies to see if this is really what it's like and if this is really what's happening when an AGN occurs. And so the two things we still need to study is how much of a balance do we need to have in order to create a perfect planet like Earth, and also how far away from the AGN a planet can be for a planet not to lose atmosphere and water. Some of the previous studies suggested that within about 3,000 light years away from the central black hole is where it becomes really dangerous for anything to survive. So basically, if a planet exists within about 3,000 light years away from the center of Centaurus A, it might not actually possess any life or water. Everything would most likely be stripped there. But Centaurus A might have planets with potential life on the outskirts. And because it's going through its AGN stage right now, it's very likely going to enrich any molecular cloud present in the galaxy that will end up creating other planets in the future. But unfortunately, that is kind of all we know for now. Hello wonderful person, this is Anton, and out there in the universe, there are quite a lot of really mysterious black holes. There's one specific type that we have never actually been able to definitely see. But there are 5 candidates, and very recently we discovered another one of the best candidates so far. So technically there are 3 major types of black holes. Well, I guess 4 in a sense. The first one, the more obvious one, and the one most of us are familiar with now, mostly because of this beautiful picture, are the so-called supermassive black holes. There's one of these black holes in most galaxies out there, although not all of them. And this is what, for example, Sagittarius A star, the supermassive black hole in the middle of our own galaxy, looks like in comparison to our own Earth. As you can see, our planet Earth is ridiculously tiny in comparison. Then we have another black hole type that we've discovered many times, the so-called stellar black holes, also known as stellar mass black holes, and this is almost the opposite. You'll notice how these are really small, and they're so small as a matter of fact that normally their size is only a few kilometers across. These black holes were discovered mostly because, as they orbit around other stars, they actually end up kind of emitting a lot of various radiation and produce a lot of energy simply because they absorb the material from the nearby star. In this case, this is the most famous example, the so-called Cygnus X1, and here, as it orbits around its partner, it absorbs a lot of mass and thus emits the energy as this mass is absorbed and ends up creating the beautiful accretion disk you see on the screen. So this is the second type. Then we have the mysterious primordial black holes, and these are the black holes that were supposed to exist since the beginning of the universe. They sort of appeared really quickly because a lot of mass suddenly collapsed into tiny points and existed ever since the beginning of the universe. But we've never seen these, and the few attempts at trying to discover these black holes have been so far relatively negative. For example, the Japanese researchers looked at the Andromeda galaxy for a pretty long time trying to discover these primordial black holes, but they haven't discovered anything except for maybe one. They expected to find thousands. And at the same time, some scientists suggested that Planet 9, for example, could be one of these primordial black holes. But once again, there's really no evidence yet, it's just a hypothesis. And lastly, there's another type of black holes that is even more mysterious than all of the above, the so-called intermediate-sized black holes. These are black holes that are normally expected to be over 1,000 masses of the Sun, but very likely under about 10,000 or maybe under about 50,000 masses of the Sun, and these are the only black holes we have never been able to most definitively observe. In terms of size, in comparison to planet Earth for example, here this type of a black hole would be maybe size of a typical gas giant, like for example Saturn or Jupiter. However, its mass would be in thousands or even tens of thousands of masses of our own sun. But because we don't really understand how these black holes are created, or if they even exist technically, we haven't really found any definitive proofs yet. But there were at least 5 observations in the last few decades where we kind of thought we saw at least 5. Now, the more famous example is actually from roughly around 2003. Back in 2003 and for about a decade, scientists were able to observe this really bright flash that was also observed in different frequencies, and having analyzed the data and specifically the actual energy output and the amount of different multi-wave energy generated, they realized that something must have been really massive to create this. And the most recent follow-up to all of this observation and analysis that was only released a few weeks ago from when I'm making this video, once again confirmed that it's very likely something akin to an intermediate black hole that was very similar in size and in mass to what you see right here, that very likely had a star that fell into it. And when a star falls into a black hole, it obviously is going to generate a tremendous amount of energy. Okay, in this case it didn't really do anything because this is just a simulation, but the amount of energy generated here suggested that this was a tremendously powerful event, and only something really powerful, but something not as massive as a supermassive black hole could have caused this. But that was the first observation of so-called IMBH, intermediate mass black hole. The other more recent observation, or actually analysis, involved a runaway star, basically a star moving really fast away from our galaxy, that very likely gained that velocity by approaching really close to intermediate black hole, or at least something really massive, but not a black hole in the center of the galaxy. One of these stars was moving so fast and was coming from such a strange direction that the only reasonable explanation scientists could give is that there was an intermediate mass black hole, completely invisible, but somewhere on the outskirts of the Milky Way. And now, only a few days ago, scientists released another paper suggesting that there is another intermediate black hole that was discovered very close to the center of our own galaxy. And unlike previous discoveries that usually dealt with either other galaxies or essentially not actually even giving us a specific location, this time we do have a very specific location where we think there might be an intermediate black hole that is once again a little bit quiet. It's not visible and it doesn't produce any energy, but there is a way for us to see it. And it involves looking at what's happening around the area where the black hole might be located. The scientists analyzing the ionized gas here realized that it was moving way too fast, and it seemed as if it was orbiting this really unusual location in the middle. And without a black hole, this is really challenging to explain. It seems like there is gas kind of moving around in a circle in an orbital kind of a motion with speeds of anywhere between 10 to even 60 kilometers per second at really far away distances. The only explanation is that there's something really massive in the center of this gas. Something equivalent to about 10,000 masses of the sun, very similar to the simulated black hole you see right here. It's just a little bit smaller in size than Jupiter, but its mass is tremendously large. Now, for all we know, this could be obviously some other really massive object, like for example, maybe this is actually our first detection of the clump of dark matter in the middle of the galaxy. But right now there's really no evidence for that. A much easier and a much better explanation is that this is once again the 5th detection of a potential intermediate black hole right here in the Milky Way galaxy. And this is actually not the first time this team discovered a similar black hole. A few years ago, they've also identified a similar black hole of about 32,000 masses of the sun using a very similar technique. In other words, it's not their first discovery and it's very likely not their last. It's possible that this team will discover a lot more of these intermediate black holes in our galaxy, and at the same time they might be the first to finally confirm one as well. As of today, it's still a candidate. We still have no actual confirmation that this is a black hole. Nevertheless, it's super exciting and I'm only looking forward to more studies from this team to find out what they actually discover next. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery about black holes coming from various dwarf galaxies. Mostly because in the past we've always believed that not all dwarf galaxies have black holes, specifically supermassive black holes. But new study seems to disprove that. Now there are quite a lot of various dwarf galaxies out there. Our own Milky Way galaxy has a few of them orbiting around us. This is the most famous one, this is the Large Magellanic Cloud, where we also don't really think there's any supermassive black hole, like the one in the middle of our own galaxy. In the last few decades, having investigated various types of galaxies out there, most scientists realized that the supermassive black holes that our own galaxy has seem to be more prevalent in larger galaxies and seem to be for the most part absent from various smaller galaxies like Large Magellanic Cloud and Small Magellanic Cloud. And pretty much most of the recent studies, including this one right here, discovered no actual large black hole in these smaller galaxies. In other words, it seems that for the most part, the presence of supermassive black holes is really limited to larger, more massive galaxies that are more well developed. But if these smaller galaxies don't have any black holes in them, and if larger galaxies are made from these smaller galaxies, how do galaxies get black holes to begin with? And so these are some of the mysteries that some of the scientists are trying to investigate, and this wonderful lady right here, Amy Raines, decided to take it a few steps further. Back in 2011, Amy was looking at this one specific galaxy where we kind of never found anything, this beautiful starburst galaxy known as HAN 2-10, and this galaxy, even though it was quite powerful and had a lot of new stars being created in it, did not seem to possess any supermassive black holes in the middle, until Amy looked at very specific frequencies using radio telescope and discovered that somewhere right there in the center there was actually a really large and really massive black hole. As a matter of fact, the mass of that black hole was not really much smaller than the one in the middle of our own galaxy, even though HAN 2-10 is a much smaller and much less massive galaxy. In other words, she realized that we just have to look for these black holes differently. So instead of looking at various galaxies in visual light, we have to start looking at them in radio light, using radio telescopes. And so this is what she decided to do with approximately 111 galaxies, more specifically smaller dwarf galaxies, where we didn't actually find anything before. And so in a recently published paper that you can find in the description below, she investigated several galaxies and discovered black holes that we've never seen before, and also discovered something really unusual about them. In short, out of 111 galaxies that she looked at, she discovered black holes in 13 of them, and they were all quite easily visible in radio frequencies. But the reason we missed them the first time is because they were not in the center at all. And if you look closely, you'll see that it's either a little bit off or completely off, and she refers to these types of black holes as the wandering black holes, which essentially correlates with a lot of other predictions from other scientists that suggested that for these smaller galaxies, it's very likely that when two or more smaller galaxies collide, their central black holes very likely get dislodged from the center and essentially end up either completely getting kicked out of the system, or in some cases end up essentially becoming wandering black holes moving around the outskirts of the galaxy itself. And from this discovery alone, we can kind of assume that a lot of other very similar galaxies probably don't have their black holes in the center either. Now obviously some of them may have lost these black holes and maybe they're actually somewhere really far away, traveling across the vast empty space of the cosmic web, mostly between various galaxies and potentially once in a while coming in contact with those galaxies. But in general, it does seem that a lot of these black holes simply become dislodged. In other words, let's just say we wanted to find where the black hole of Large Magellanic Cloud was located. Well, we've only looked at the center. We haven't really looked as thoroughly in the outskirts, and we definitely have not used the radio telescopes to look at those outskirts as well. So it's very possible that similar studies will discover where the central black hole, or I guess it's actually not even the right word anymore, where the supermassive black hole of this galaxy is located. And this also applies to other similar galaxies, specifically Triangulum Galaxy. This galaxy here, if you didn't know, is actually one of our closest and largest neighbors. Almost everyone knows about the Andromeda Galaxy, but very few people know about Triangulum, which is also quite easily visible in the night skies and is also not so far away from us. But this galaxy, unlike other similar galaxies, does not seem to possess a central black hole either. So it's possible that this galaxy also has a black hole somewhere on the outskirts, the so-called wandering black hole. Also, a few months ago, we've talked about this unusual discovery in the Milky Way galaxy, where one of these scientists discovered that something passed through the Milky Way and disrupted it in a major way, and we don't really see what it is or where it went. Some scientists thought it was dark matter, but some scientists thought that it was actually one of these wandering black holes, which essentially means that there could be billions and billions of these really massive, really powerful, and extremely dangerous black holes traveling across the intergalactic space. All of these are a result of various galactic collisions, and some of them might also interact with typical galaxies like the Milky Way once in a while. We obviously have no evidence of this yet, and we don't really know what happens when these black holes interact with galaxies, but because we've seen at least one sign in the Milky Way, and because we know these wandering black holes seem to be everywhere, it's definitely something interesting to consider. And so all of this, of course, means that there's still so much to learn about these massive giants traveling across the universe. But I think another major surprise in this study is the total mass of these black holes. None of them were really that small. As a matter of fact, many of them were very, very close to the mass of the black hole in the middle of our own galaxy, suggesting that even in these smaller, much younger galaxies, somehow the black holes managed to grow really big, really fast. And right now, other than trying to use computer simulations, we can't really explain this very easily, because even though we can kind of explain why these black holes are dislodged, usually because of the collisions, explaining why they're so massive is a completely different story. We don't really know how they got so much mass so quickly. But other than that, that's really all we learned from this study. I think the most interesting thing here is, of course, the idea of these wandering black holes. These really massive objects just kind of flying through space, minding their own business, until of course they decide to collide with a galaxy, or maybe two. Let's actually see what happens if we try to collide a very massive black hole similar to Sagittarius A star with these two dwarf galaxies I created. Now, once we discover more about this, I'll make sure to follow this up with another video. But until then, that's kind of all we know. It's a very interesting study, but not really a study that resolves questions. It's a study that creates more questions. We now know that a lot of galaxies that we thought didn't have black holes have them. Hello wonderful person, this is Anton, and in this video we're going to be talking about this new study that may have actually created a little bit of a problem for physics. In discovering that when it comes to three orbiting black holes, it creates a paradox we can't really explain. Now before we go into black holes and before we go into understanding what the study is about, I need to briefly mention the so-called idea of arrow of time or time symmetry. So when it comes to time, the idea of time, in physics we believe that it can actually be reversed. It can either go forward or it can go backwards, which in some sense I guess is not really difficult to imagine. What is however difficult is identifying which way is time flowing. For example, right here in this simulation, can you actually tell if this is running forward in time or if this is running backwards? There's actually no way for us to tell, because everything that's happening here could technically be going either way. But one way of identifying what the direction of time is by introducing the idea of entropy. Now this is a really complex topic we're not really going to cover in this video, mostly because there's a lot of things to talk about, but entropy is the fundamental law of physics, the second law of thermodynamics specifically, that explains the arrow of time in terms of chaos. Basically, with time, the universe should be increasing in entropy or chaos as opposed to decrease. So in other words, today the idea of heat transfer, or going from hot to cold, is essentially explained as the transfer of entropy or the increase of entropy in the universe. So going back to our original simulation here, we can actually see which way the entropy is flowing to determine if this is going backwards in time or forwards in time. So here, if I were to place the moon much closer to Earth, because of the tidal interactions between the moon and the Earth, if this is going backwards in time, we should see a lot more order, but since this is going forward in time and not backwards, you can see that the entropy is increasing and the moon is becoming more and more disorganized. So this is one of the ways of determining the so-called direction of the arrow of time. And here, even every explosion is adding even more entropy to the planet and to the system as a whole. But that's a very simple way of explaining this, and in reality the concept of entropy is a lot more complex. But it is fundamental, which is of course why we always believed that the time is also symmetrical or reversible. But we also had some unusual phenomena that we've discovered that could not be explained with symmetrical time. One of them is in regards to black holes. The most famous concept here is of course the idea of information paradox. So the way it goes is as follows. Let's say that you as a person, or whatever, your book or your laptop that possesses information and knowledge, is slowly falling into the black hole. And essentially at some point it's going to cross the event horizon, and we know that nothing can escape the black hole, which of course means that essentially it goes in and kind of slowly gets destroyed. So all of the information from your laptop, about your laptop, and of course if you were falling with your laptop, about you as well, is now technically gone forever. Basically, it's gone into the black hole. But this violates the principle of time symmetry, Because as I just mentioned, most of the physical concepts depend on the idea that you can reverse time and go backwards. Essentially, we should be able to reverse time, and if we were to go back in time, see that your laptop and you with your laptop and whatever else fell into the black hole is now recreated back as it used to be. But this is not something we can do with black holes because, by definition and by design, they don't seem to contain any information in them. They don't seem to contain any information about the structure of your, for example, particles that you made of. And so all of this information, if you were to fall into the black hole, would be lost. So this is what we, in a nutshell, call the information paradox. And even today, it's still kind of unresolved. Mostly because we've always taken this time symmetry for granted. And it actually does, of course, make sense because, well, technically by looking at the events today and at various things happening in the universe, we're able to work backwards and understand what happened in the past. So that's the idea of time symmetry or time reversal in a nutshell. But now, scientists whose paper you can find in the description below discovered another unusual phenomenon that seems to violate this time symmetry yet again, and it does involve black holes once again. This paper right here actually decided to investigate things a little bit differently, using computers. And the idea here was actually not too complex. Take 3 really massive black holes, or the simulation of these black holes, and place them in orbit around one another, having the simulation run for a very long time, but also at the same time, once in a while stop the simulation and then reverse the time to see if there was any difference in what was originally created. If we were to use this as an example, they ran the simulation once this way, forward time, and then they reversed the time to see if the final result of the reverse time simulation was exactly the same as the original result from the first simulation. In other words, they were testing for time symmetry. But unlike in this simulation that we have here, which only has 2 bodies, which is relatively easy to calculate, this is Newtonian physics, they chose a 3-body simulation. As of today, unfortunately, the 3-body problem has not actually been solved. It does not have a general solution that can apply to everything, mostly because with time the system becomes way too complex and the amount of chaos that's introduced with every interaction increases exponentially to the point where it becomes ridiculously difficult to predict. Here's actually one of the last papers I was able to find that tries to find a solution to some of the more complex 3-body simulations. But even here, if we were to apply this to, for example, the solar system, we could only really calculate what would happen to the system up to about 1 million years maximum. So as an example, let's take these 3 Earths, place them around one another, disable collisions, and see what happens to their orbits. Here, as they start orbiting around one another, the actual orbits will become more and more chaotic with time. It's going to be extremely difficult to predict what's going to happen with these 3 planets in approximately 5 minutes from now, not to mention 5 years or million years. So this is why the 3-body problem is still one of the most sort of fundamental unresolved problems in orbital dynamics. And this is kind of what they did, but with 3 black holes, mostly because it allowed them to use much more massive bodies. But in this model, they also introduced the idea of chaos. So here, because of the length of the interaction, as these bodies orbited around one another more and more, they essentially started to produce more and more chaotic interactions. And the amount of this chaos is represented right here, starting from the smallest possible length, which is the Planck's length, the smallest possible distance in the universe, and eventually with time, as the time progressed, you'll notice that the actual interaction here will get even more chaotic, increasing the deviation exponentially. And it's going to be seen in this simulation on the right as the kind of a white line that will start appearing as the simulations deviate from one another more and more. And here, after approximately 30 to 35 million years, the actual deviation becomes already size of planet Earth. And you'll see that this will actually cause visible differences within about 35 to 40 million years after the initial simulation. And so this is really important because what this essentially shows us is that within a 3-body simulation, just a simple natural simulation that occurs everywhere in the universe, with time due to simple chaos and unpredictability of what's going to happen in the future, we're going to reach a very similar idea to the information paradox. The arrow of time becomes irreversible, or if you were to reverse it, you would actually end up in a completely different situation from what you expected. Which in their simulation is visible with the red and white color. So the red is the original simulation, white is what ended up happening after the time was reversed. And that unfortunately creates a huge problem for physics, because currently we don't really know how to explain any of this. A lot of the modern physics, a lot of the fundamental physics depends on the idea of time reversibility or time symmetry, so time has to be reversible. Entropy, by definition, is defined as time that can be reversed. But if in reality, because of the entropy itself, because of the chaos itself, time becomes irreversible, we're gonna have to rework some of the physics, and that unfortunately is not really that easy. Now, I'm sure more follow-up studies will probably introduce some of the explanation here. Right now there is really none. It seems that the scientists behind this paper do think that this is a natural, fundamental problem that's caused by the chaos itself, the chaos of the universe, and various chaotic systems that are formed when you have a three-body simulation. And fundamentally what this of course means is that it's almost impossible to predict what really happened in the past. And even though originally I thought that maybe it was the simulation, maybe it was because of the actual computer simulation they used and the limitations of the computer itself, other studies that use a similar simulation to, for example, try to mimic the orbit of comet Halley, or to use it for some other similar predictions, did actually establish that this is an extremely accurate simulation, with the main errors being the general chaos of the orbital parameters themselves. In other words, it's nothing to do with the simulation, as much as the universe itself having these chaotic errors that are introduced with time. Now, we do need to have a lot of follow-up studies, of course, and we do need to actually have a more, I guess in some sense, acceptable explanation to what's happening here, but right now, the way that it seems is that the arrow of time is probably not symmetrical after all, at least because of the chaos introduced through various systems. And it also suggests that trying to see back in time and to recreate something with extreme precision becomes basically impossible, simply because of the nature of the universe and all of the chaos that makes this a practically impossible task to achieve. And this is exactly what this paper is trying to explain in a nutshell. And the more particles we get, the more unpredictable it becomes. And this unpredictable behavior seems to be the foundation of the universe itself, which of course only means that we can know the universe only to some extent. We can unfortunately never really know what exactly happened back in the days, or more specifically, we can never really certainly know something in the future either. All of this chaos makes things completely unpredictable with time. So in other words, what all of this means is that the universe has a limit in accuracy. And so what black holes have actually taught us so far is that it seems that uncertainty is the only certainty.